And we're back, and now we're covering double and triple covalent bonds, which should actually be a lot easier for you guys to understand. So, not easier, but it'll start jiving with you. If you get the single bonds, then these should make sense. Double bonds have 2 pairs or 4 electrons shared, and triple bonds have 3 pairs shared. So this usually occurs when there is a shortage of valence electrons that are available for bonding to make all of your octets. So for example, oxygen, we're going to make O2. First thing we do is step 1, we count our valence electrons. So we know that each oxygen has 6 valence electrons, and there's 2 of them here, so it'd be 2 times 6, which is 12. Now our honk rule for oxygen is 2, and so we have 2 times our oxygen, big O, that's going to equal a total of 4 bonds. But if we're going to divide that by 2, because they get shared, that's 2 bonds. How are you going to make 2 bonds between 2 atoms? Well, this is called a double bond. You have a big oxygen here, and then you're going to draw 2 pairs of electrons, then another oxygen. And then the other electrons scatter around it like this. And they actually do look like they're on the corners here because they want to stay away from this double bond. But here you go. Here's an octet for the one oxygen. Here's an octet for the second oxygen. And you have this double bond there. Okay, the 2 pairs of shared electrons. Okay, CO2 is going to be similar. We find our electrons, that's 4 electrons from the carbon, and another 12 electrons from the oxygen, and we get 16 total. Our honk rule, however, says that carbon needs 4, and we need another 2, plus another 2 from our oxygen, so that's a total of 8. Divided by 2 equals 4, and that's 4 bonds that we need between our carbon and our O2. We know that carbon goes in the middle, because it always goes in the middle. Okay, but here's tricky. You have to make 4 bonds here. Okay, well, and we know that carbon needs 4 bonds. So it is actually going to be 4 bonds with the carbon. It's happy because it has its octet. Okay, and our oxygens are going to bind that also and have its lone pairs out to the side. And this is what carbon dioxide is going to look like according to our Lewis dot structure. And both of these are linear molecules. They make lines, straight lines with their molecules. Right. Now let's try C2H4. We tried C2H6 before, and we had hydrogens everywhere. Well, this one's going to have to be different. C2H4, we count our electrons. 2 times 4 is 8. 4 times 1 is 4. That's a total of 12 electrons. But our honk rule says that there's 8 bonds for the carbon, plus 4 bonds for the hydrogen. That means 12 bonds. Divide by 2 equals 6. But we know that each hydrogen is 1. That leaves 2 for the carbons. So our carbons are going to go in the middle, and they are going to have a double bond between them. And then we have bonds for our hydrogen. And they actually do sit on the corners like this. Okay, and that's how this is going to make it. Notice the double bond in there. All the hydrogens have their 2 electrons. All the carbons, both carbons have their 8 electrons, and that's how you make your ethene molecule. Now, we even have fewer electrons here, and you can go through the math, and we can walk through it. But the primary idea is this is going to wind up being hydrogen, carbon, triple bond, carbon, single bond, hydrogen. Okay, and if you're struggling with this one, be sure to contact me and I can walk you through it. But it's pretty much the same idea, that you're going to have 8 bonds for your carbon and another 2 bonds for your hydrogen. Total of 10 bonds. And a total of 10 divided by 5 is 5 bonds. for 10 electrons. All of those electrons have to be bound in there. Now we get into Lewis dot structures of polyatomic ions, and these get to be a little tougher. Because now we need to remember that our polyatomic ions, we're going to have to add or remove electrons based on the charge of the ion. Okay, sorry, I had to skip there and slide up a little bit. We're going to have to add or remove electrons based on the charge of the ion. So we add and then we add brackets around the Lewis structure to show that it really is the charge of the entire ion. So here's our first example. We're going to do ammonium. Ammonium ion. And we're going to identify our electrons. Nitrogen has 5. Each hydrogen has 1. There's 4 of them. So 5 plus 4 times 1. But, see this positive right here? This positive means that somewhere in there we have 1 less electron than a neutral compound. And so we're actually going to subtract an electron from this total, okay, because we have a positive ion. And that winds up as being 5 plus 4 times 1. So that's 5 plus 4 is 9 minus 1 equals 8 electrons. But we still have to obey our honk rule. And our honk rule tells us that our nitrogen is going to require 3 bonds, and our hydrogens are going to require 4 bonds. How's this one? Okay, so this is actually a total of 7 bonds. Now, some of you may be asking yourself, how are we going to deal with 7 bonds if we have to divide by 2 at this step and give us 3.5 bonds in our compound? Well, here's the trick. Remember that minus 1 electron that we lost? Well, if we lose an electron, that means that we are probably going to lose one of our bonds here. That goes away. Now this gets a little tricky because here's our nitrogen. Our nitrogen is going to have 5 electrons, but we only have 8 to work with. We have to have 4 hydrogens. Well, here's a hydrogen. Here's a hydrogen. Here's a hydrogen. We have all 8 electrons. But remember, we lose the positive ion. We can attach a hydrogen to that lone pair on the ammonium, and all of a sudden we have our ammonium plus 1 ion. Okay, and here we are with carbon. This is a new one. This is called carbonate, CO3 2 minus, and the same rule applies. This carbonate, our honk rule, there's 4 bonds for the carbon. And there's going to be 2 bonds for each of the 3 oxygens. So it's going to be 2 times 3. Okay, so that's going to be a total of 10. 2 times 3 is 6 plus 4 is 10. We'll divide that by 2, which means we need 5 bonds in our molecule. Now, carbons always go in the middle, and carbons are always going to need 4 bonds. Okay. However, since we are adding 2 free electrons, those are going to occupy, those 2 electrons are actually going to take away one of those bonds because we have extra electrons lying around. So here's what's going to happen. Carbon's going to go in the middle, and we have 3 oxygens around it. Oxygen, 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 and oxygens will go around the carbon. Carbons are always in the center. Oxygens are rarely in the center. We know that carbon's going to need 4 bonds, so one of these oxygens is going to get a double bond. So I'm going to draw it over here. And then we're going to add in the rest of our electrons. Now, normally we would not have enough to do this, but if we have these 2 extra electrons, all of a sudden we've got 24 to work with rather than 22, and we can get our full octet from our oxygens right here. And this whole thing will carry a -2 charge because we added 2 electrons. There's a 2 minus right in there. Okay. I want to amend what I said up here. Because we're able to, we have to take away a positive, we have to take away an electron. This original 3.5 bond, well, if we have to take away an electron, this is going to go up to 4 bonds rather than down to 3. That's my mistake from earlier. And it's because we take away an electron, we're going to have to find another way of sharing them. And so this is actually going to make our odd bond number go up to 4 rather than, say, 3.5. Down here, because we added 2 electrons, we needed to share 1 less bond, and so we were back at 4 again. So if you have issues with that part down here, let me know, and I can explain with this part down here, and I can explain to you in better terms about the honk rule and adding electrons or taking electrons away, and how many bonds it's going to make. Okay, but here I'm going to show you guys an easier way finally to start drawing these things. Okay, we have, instead of doing dot structures, we can do dash structures. And this is going to make making our bonds so much easier. Bonding electron dots can be replaced with a dash. So a single bond that has 2 dots is going to be 1 dash. A double bond that has 4 dots is going to be 2 dashes, and triple bonds that have 6 dots are going to be 3 dashes. So our example now is carbon dioxide. So instead of having all those dots in there for carbon dioxide, this is really just going to be O, double bond C, double bond O. And if you want to include your electrons, then you draw your extra electrons, your lone pairs, over on the side. This is going to be so much easier. For example, remember that triple bond one with H triple bond C? It's going to be H bond C triple bond C dash H. Doesn't that just make it so much nicer? Okay, we had ethanol before. I challenged some of you guys to draw ethanol, which was the C2H5OH. Well, that's just going to become CCOH, H, 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 H. Instead of having to draw all the dots all the way around all those, that does need 2 dots right there. Instead of having to draw all those dots, we can just draw the single bonds, and that makes it so much nicer. Okay, and eventually we'll be able to drop these extra lone pairs also, because you'll remember that they're there. Okay, this brings us to bond dissociation energy. Bond dissociation energy is the energy required to break bonds. Okay, the shorter the bond, the stronger the bond, or the higher its bond dissociation energy. Okay, the more bonds there are, the closer the 2 atoms are held together. And so triple bonds have a higher dissociation energy than double bonds, which are higher than single bonds. See, we also have resonance structures. Now, you may have noticed that with the carbonate, the CO3 2 minus, that's this one, it's CO3 2 minus, the one that we did at the bottom of the previous page, it can actually be drawn one of 3 ways, where you can have the triple bond between this oxygen, between that oxygen, or between that oxygen, and all 3 of those oxygens would be different. Oh, that reminds me, we need to go back for a minute, because I drew this wrong. So we're going to pause this and go back. Down here at the bottom, I goofed, and I need to apologize to you guys. So, some of you may have noticed that this oxygen right here has 10 electrons around it. Those last 2 should not be there. And whichever oxygen has the double bond does not have the extra 2 out here on the other side. So we come back over here, and we talk about what's called a resonance structure. We see that this double bond can actually rotate between any of the 3 oxygens. And one of those, and these are all equivalent locations. They're all equivalent structures. This is called a resonance structure. Right now, another question. What type of bonding goes into Na2CO3, that's covalent and ionic. But I want you to tell me why, and I want you to write that over on the side. Before we get to our last part, which is the exceptions to the octet rule. So I want you to pause here and write why those bonding types are covalent and ionic. Okay, and we're back. And what types, so what bonding types are in Na2CO3? Well, this is a metal. Okay, so your Na, okay, you have two Na pluses right there. Sodium is a metal. It makes a cation. This is an ionic compound. However, this CO3 right here is a polyatomic ion. CO3, 2 minus, is a polyatomic ion. And so that's this thing right here. And you're going to have two sodiums that are going to be attracted to 2 minus on that charge. And so the 2 pluses are going to be attracted to 2 minuses. That's what's going to make this a balanced compound, even though it has this covalently bonded polyatomic ion right there. Okay, so now we move on to the exceptions to the octet rule. Okay, so the exceptions to the octet rule, sometimes atoms can have more or less than 8 valence electrons, but these are unusual situations. One of them is boron. Boron is one of our semi-metals, and it only has 3 valence electrons, even though it can behave like a non-metal. And so when it does that, it will covalently bond with an extremely electronegative element like fluorine here that essentially rips these electrons away, and it separates themselves and it pulls them in 3 directions. And so boron is going to have 3 plus 3 times 7 electrons for a total of 24. All right, and all of a sudden boron, instead of having 8 electrons around it, it's really only going to have 6 electrons around it. But it's forced to be satisfied with that because it's forced to be satisfied with that because the fluorine isn't going to share any of its electrons with it. And the same thing here for xenon tetrafluoride. Xenon actually has 8 valence electrons plus the 4 times 7 for the 4 fluorine. And it looks like this, and this is kind of funky. This is actually a square molecule. Okay, so you have this tilted on the side, but this actually winds up being a square molecule with a couple of electrons going up like that and a couple of electrons going down like that, forcing these guys out to the side. It's actually a pretty cool molecule, a xenon tetrafluoride. And not only that, but xenon is a noble gas, so it's an exception to the noble gas rule as well. All right, and that brings us to the end of section 8.2, and we'll stop there, and you guys can, we'll finish working on this stuff next time. See you later.